Hello, this is Britt Caswell with another example video. In this video, I am covering example 2 from section 4.1 in the SavvasRealize Algebra 1 textbook. In this example, we are looking at how to graph systems of equations that have infinitely many solutions or no solutions. Now recall, when we have a system of equations, which means we're looking at two or more equations, a solution is where they intersect. Alright, so we're going to start just by graphing A here. I'm going to do this bottom one first because it looks really easy to graph it. All that I need to do is put this in slope-intercept form. So I need to put the negative 3x first and then the 5 second. So I'm just going to rearrange the order of those terms. And now this blue line is in slope-intercept form. So I'm going to rise by 5 because it has a y-intercept at 5. And then with a slope of negative 3, I'm going to fall by 3 and run by 1. And I'm going to do that a few times. Now usually when I go to graph this stuff, I usually recommend putting it in slope-intercept form because I find that that's easier to graph. But we can graph it from standard form if we want to. On this orange equation, I'm going to go ahead and do so. I'm going to graph it in standard form. So remember, to find your y-intercept, your x-intercept, you set your y equal to 0. And then to find your y-intercept, you set x equal to 0. So I'm going to do that for both of these. So I get 15x plus 5 times 0 is equal to 25. Now 5 times 0 cancels out, so I get 15x equals 25. And so I'm going to divide both sides by 15, not by 25. Got that 2 in the brain there. And I get x equals 5/3. That's kind of hideous. Let's go ahead and try it for our x-intercept. Our y-intercept. So here I'm going to set the x equal to 0 and leave y by itself. So here 15 times 0 goes away, so I get 5y is equal to 25. And if I divide both sides by 5, I get y equals 5, which is a lot cleaner. Now this point, 0, 5, that's the same point that we had on the blue line. So now let's go ahead and let's take a look at 5/3. Now 5/3 is the same thing as 1 and 2/3. So if I go 1 and 2/3, it's somewhere around here, which if I had drawn my blue line properly, right, it falls by 3 and runs by 1. So really this went 1/3, 2/3. So it's on the same spot as this blue line. So when I go to draw this, the orange line and the blue line, they overlap. And so when you have overlapping lines like this, you get infinitely many solutions. And that's because since the lines overlap, anywhere that you look on the line, it's a solution, because what's on one line is on the other one. That's why there's infinitely many of them, because lines continue on for forever. So what you're looking for, when you're looking for infinitely many solutions, you're looking for the same slope and the same y-intercept. Alright, so that's your b value, remember. So I could convert the orange one into slope-intercept form, and you'll see it's the same line. Alright, so let's go ahead and let's try this one. So my green equation is almost in slope-intercept form. It just doesn't have the y by itself, it has the 2x on the wrong side. So I'm going to add 2x to each side of the equation. So I get y equals 2x plus 6. So my y-intercept is 6, and then a slope of 2 means I rise 2 and run 2. Gives you a line that looks roughly like this. Now while I'm drawing this, it's worth noting that graphing only gives you approximate solutions. Unless your answer is a whole number, putting it on a graph is going to get you just what you kind of think it is. For one thing, because if you're graphing by hand, you have wiggly lines all over the place. You don't know what's going on. But also, if you have something like 3/8, for example, it's hard to tell if that 3/8 is 3/8 or 1/2, or it's eyeballing things. So there's other ways that we're going to learn to get exact solutions, and we'll learn about those in my future videos with substitution and elimination. So here I need to get y alone, so I'm going to add 4x to each side. So I have 2y equals 4x plus 8, and then I divide by 2 on both sides and get y equals 2x plus 4. So here my y-intercept is at 4, and then my slope is also 2. So I'm going to rise by 2 and run by 2, or sorry, run by 1 over and over and over again. Now hopefully, I mean these lines are so close to each other, hopefully it'll be clear that these are running parallel to each other for you guys. Do you guys see that? That if these lines continue on for forever, they'll never touch? So because these will never cross, because they're parallel, there will be no solution. And so what you're looking for with the slope-intercept form here is you're looking for the same slope, but you're looking for a different y-intercept. Those are kind of your key features to look for. So let's go ahead and let's try this one out. So here in the red, this is already in slope-intercept form, which is nice. So I can graph it right away. 5, 6, 7, so that y-intercept is at 7. And with a slope of 1/2, I'm going to rise by 1 and run by 2. So there we go, that's the slope. And so now this other line is not quite in the form that we need it in. So I need to get the 8y by itself. So I'm going to subtract 4x from both sides of the equal sign, so that I get negative 8y equals negative 4x plus 12. And then I'm going to divide both sides of the equation by negative 8. So I get y equals negative 4 divided by negative 8 is a positive 1/2. And 12 divided by 8, I'm going to have a negative, let's see, those are both divisible by 4, so 3/2. So here we are, I'm at negative 3/2 for my y-intercept, and then again I have a slope of 1 over 2, so I'm going to rise by 1 and run by 2. And so here it's kind of hard to graph, you can see, because I have to make sure that I'm at the halfway marker on everything. And so that can be really kind of tricky to graph properly when I go to graph. So I mean, just from eyeballing it, it looks like these things run parallel, so it looks like there's no solution. But we always want to check out our slopes and to verify that. Now remember, if they have the same slope, that's how you know there's no solution. So here's a slope of 1/2 and a slope of 1/2, and our y-intercepts are different. So this is in fact no solution. Now if the slopes are not the same, they'll eventually run into each other. It's just you might need to zoom your graph in or out, or adjust your scale. All right, let's try one more. So here we need to get our y alone to graph it. So I'm going to subtract 3x from each side. So I have 2y equals negative 3x plus 9. Sorry if you can hear my cat losing his mind in the background. He's having a great morning. So now I'm going to divide by 2. So I have y equals negative 3 halves x plus 9 halves. And that's a bummer to have to graph. That's a mess. Alright, so 9 halves is like 4 and a half. And the slope of negative 3 halves means I'm going to fall by 3 and run by 2. Fall by 3, run by 2. Alright. I'm going to hope that I drew this long enough on the graph to run into an intersect. But those little half measures, they can be kind of a bear. So you could do stuff like adjust your scale on your graph so that like maybe each tick mark is a half. Desmos is really useful for that as well. So now here, all that we need to do is we need to get rid of that 2/3 that's in front of the y. And so remember, to get rid of a fraction, what I'm going to do is I'm going to multiply both sides of the equation by what's called the reciprocal. So I'm going to flip the fraction upside down and multiply the equation by that. So 3 halves times 2/3 is 1. So I get y equals, now 3 halves times 3 is 9 halves. And then minus, and then 3 halves times x is 3 halves x. And then our last step, we need our x term before our constant. So I'm just going to rearrange the order of the equation. Now by doing this, you can see that the red equation and the blue equation are, in fact, the same equation, which is nice. And so I'm just going to draw the blue line overlapping the red line and not go wild. So because they are the same equation, that means that we have infinitely many solutions. Alrighty, so there we have it. That is solving systems when there's infinitely many or no solutions. Until next time.